Assalamu alaikum. We have the pleasure today to have as speaker Professor Skander Hachicha from King Faisal University. Prof. Hachicha obtained his PhD thesis from Tor Vergata University of Rome, Italy in 2006. From 2007 up to 2023, he was assistant professor, associate professor, and professor at the University of Tunis Al Mana. And from September 2023, he is a professor at the King Faisal University, Saudi Arabia. The topic of research of Professor Hachicha are around the classical and quantum approach, probability theory, stochastic analysis, Markov chains, quantum Markov semigroups, invariant state, and convergence to equilibrium of QMS. Today, the talk of Professor Hachicha is entitled on reducibility and positivity improvement of norm continuous quantum Markov semigroups. Thank you again, Professor Skander, and please you can start your talk.
Thank you. Assalamu alaikum. Today we speak about the notion of irreducibility and positivity unproven and the relation between them of norm-continuous quantum Markov semigroups. The plan of this talk: first, you speak the notion of quantum Markov semigroup. After that, the positivity improvement of quantum semigroup, of quantum Markov semigroup. After that, you study support projection of state under the action of quantum Markov semigroup, and you discuss the example of channels or discrete time case. This example is irreducible, but not positivity unproven. And finally, you prove the equivalence between irreducibility and positivity improvement under some condition. From a physical point of view, quantum Markov semigroups were introduced to model the irreversible evolution of an open quantum systems and are now an important tool to investigate quantum systems and stochastic process. There is many applications of quantum Markov semigroup, for example, heat conduction in quantum mechanics, quantum optics by using master equation, quantum theory of the information, and finally, but not finally, oscillator harmonic by using stochastic Schrödinger equation. From a mathematical point of view, quantum Markov semigroup is the generalization of a classical Markov semigroup. The first is defined in C-star algebra, is non-commutative case, and the second is defined in function space commutative case. So, what is C-star algebra? A C-star algebra is a Banach algebra A with involution denoted by star with the following properties. The star of lambda A plus mu B is equal to the conjugate of lambda A star plus the conjugate of mu B star. The star of A is A, the star of AB is B star A star. The star of A star, the norm of A star A is the product norm A star. This is a C-star algebra. For example, the algebra of all bounded operator on H provided with the involution or the adjoint defined by for any bounded operator A associated A star satisfy the dot product AX Y is equal X A star Y for every X Y in H. BH is a C-star algebra. In 1943, Galfond, Nairman, and Schneider proved that any arbitrary C-star algebra A is isomorphic star a C-star algebra of bounded operator on a Hilbert space. So in this talk, you speak only the set of all bounded operator on a Hilbert space. Now, there is many topology can be defined through the convergence of nets. Let X alpha be a net in BH and let X be a bounded operator. You say that X alpha converges weakly to X if the dot product Vx alpha U converges to the dot product Vxu for every Vu in H. You say X alpha converges sigma weakly to X if the sum of the dot product Vn X alpha Un converges to the sum of the dot product Vn X Un for every seconds Vn En square summable of H. You say X alpha converges strongly to X if the norm of X alpha U minus XU converge to 0 for every U in H. Finally, you can define converges sigma strongly to X if the sum of the square of the norm X alpha minus XUN converges to 0 for every seconds UN square summable of element of H. Now you define the state. The state is the generalization of probability measure. Let 1 be the identity operator of PH. A state phi as a linear map defined on PH with value in C satisfy positivity phi I star A is positive for all bounded operator A in BH, and normalization phi of the identity is equal 1. Now, if H is separable Hilbert space, so there exists En orthonormal basis of H for all positive bounded operator X, you can define the trace of X as the sum of the dot product En x En, and this sum is independent of the choice of the orthonormal basis of H. Now, you can define the trace class operators. The set L1H is the set of all bounded operators such that the trace of absolute value of X defined by trace of the square root X star is finite. So, if X in L1H, you can define trace X. You say that every bounded operator can be written combination of positive bounded operator. Now, example of a state, if you take rho density matrix, that is mean rho is a positive bounded operator such that trace of rho is equal 1, you can define the state phi, define it on BH with value in C, such that for all bounded operator A associated trace of rho A. And you can prove if H is separable Hilbert space, so any state phi can be represented by density matrix rho. That is mean for every state phi there exists density matrix rho such that phi A is equal trace of rho A. Example of the state of this example, you can define for all UV in H the operator bracket UV defined by the bracket UVW is equal to dot product VWU. So you can define the pure state associated to U by for every bounded operator associated the dot product EU is equal trace of the A, the bracket UU. This is called a pure state associated to the vector U. Remark clearly, we can prove X alpha converges sigma weakly to X if and only if for every density operator rho, trace of X alpha rho converge to the trace X rho. Now, with this table, you give you the connection between Kolmogorov probability and quantum probability. In the sample case, when omega is the finite set, Kolmogorov probability is represented by the triplet omega Fp. Quantum probability is represented by the triplet H, Ph, rho. H is the Hilbert space, PH is the set of orthogonal projection on H, and rho is the density matrix. Now, the elementary event is represented in Kolmogorov probability by the singleton WK. In quantum probability is represented by EK. Here, the omega is the finite set W1, W2, etc. Wn is represented in quantum probability by H is Cn when n is the cardinal of the omega. Event space F is represented in quantum probability by pH, the set of orthogonal projection on H. Probability measure is represented in quantum probability by the diagonal matrix P1, P2, etc., Pn, when Pk is the probability of the events Ek, and the probability of the events Ek in quantum probability is the trace of rho Ek. Now, random variable x defined in omega with value in C is represented in quantum probability by the diagonal matrix xw1, xw2, etc., xwn. Finally, mean values or expectation is the sum of pk xwk in quantum probability. This is the trace of rho x. Now, what is the quantum Markov semigroup? A quantum Markov semigroup in the algebra PH is the one parameter family TT such that T0 is the identity map on PH, TS is T plus S, TT of the identity operator is equal identity operator, TT is completely positive. This is the generalization of positivity in the commutativity case. That is mean for any T and for any integer n and n, all n tuples of operator xg, yg, g between 1 and n, you have the sum of xg star, tt, yg star, yk, xk is positive. Weak star continues. That is mean for all the trace class operator or density matrix W in H, and for all bounded operator, the limit when t go to 0, trace of WTTX is trace WX. And finally, for all t and all net x alpha converge to x in the weak star topology, limit of TTX alpha is equal TTX. This is a quantum Markov semigroup. Like the classical case, you can define the infinitesimal generator of a quantum Markov semigroup T is the operator L, whose the domain DL is the set of all bounded operator A, such that the limit when T go to 0 of TTA minus A divided by T exists in the sigma weak topology, and with this limit you can define LA is equal to this limit. As a consequence of complete positivity, the generator of norm continuous quantum Markov semigroup, that is mean the limit when t go to 0 of C prime of norm TTX minus x, when norm x is less or equal 1 is equal 0, have a special form called Goroni, Kozovsky, Sotrachan, Limblad, GKSL representation, described by the following result. So, GKSL representation, let L be a generator of norm continuous quantum Markov semigroup on BH. Then there exists a bounded self-adjoint operator H and a finite or infinite sequence LL of element of BH, such that the sum of LL star and L is a strongly convergent sum. And if you take CL square summable sequence, such that C0 plus some CLL is equal 0, then CLL is equal 0 for all positive L. And you have the following representation of L. Lx is equal I, the commutator H, x minus 1/2, sum of LL star LLX minus 2 LL star XLL plus X LL star L, when commutator HX is equal HX minus XH. If you write G is equal minus 1/2 sum LL star LL minus I H, so LX can be writing G star X plus sum LL star X LL plus XG. This is the GK cell representation is proved when the quantum Markov semigroup is non-continuous and completely positive. Now, the new result of this talk, you showed that for a non-continuous quantum Markov semigroup, irreducibility and positivity improving for any strictly time t positive are equivalent under some general condition. That hurt. Definition of the positivity improving. Let A be an operator in BH. You say that A is called positive if for every vector different to 0, x, the dot product x is positive. And you can write A is greater or equal to 0. You say that A is strictly positive if the dot product xax is strictly positive for any vector x different to 0, and you write A is strictly positive. Now, a quantum Markov semigroup is called positivity improving if for all bounded operator A positive and not identically 0, you have TTA is strictly positive for each strictly positive T. This is the definition of positivity improving. Now, you can define T star, the pre-dual semigroup of T, defined in the set of density matrix by trace of T and X star T W X is equal trace of W T T X for all bounded operator X and for all density matrix W. You can prove any density matrix can be writing in the conventional basis sum of WG, the bracket psi-G with omega G is positive and the sum of omega G is equal 1. So you can define the Sipora projection of the state W is the closure of the span generated by the vector psi-G with a G in G such that omega G is strictly positive. With this notion, you have this result. For a quantum Markov semigroup T on BH, the following are equivalent. First, T is positivity improving. Second, for all pure state psi and all strictly positive T, the Sipora projection of the state T and X star T of the bracket psi is H. The proof of this, if T is positivity improving, then for all E psi in H with the norm psi is equal 1, and for all strictly positive T, you have TT of the bracket E is strictly positive because the bracket E is not identically 0 and the bracket E is positive. The operator bracket E is positive. So the trace of the bracket T and X star T of the bracket psi is equal this dot product is equal to the dot product of the psi TT of the bracket psi, and this is strictly positive. So E is in the Sipora projection of the state T and X star T of the bracket psi, and this is for every vector E in H. So H is included in the Sipora projection of the state T and X star T of the bracket psi. Conversely, if the Sipora projection of T and X star TT of the bracket psi is H, so you can take for every positive bounded operator X, you have trace of X T and X star T of the bracket psi is equal to dot product psi TTX psi, and this is strictly positive because the Sipora projection is H. So T is positivity improving. This is the first new result. Now, you give you the notion of irreducibility of quantum Markov semigroup, introduced by Fagnola Redoledo in 2002. And this notion is important to study the quantum Markov semigroup and eases the natural generalization of irreducibility in classical case. Definition of projection P in pH is called subharmonic if TTB is greater or equal to B. You say subharmonic if TTB is less or equal to B, and you say this is harmonic if TTB is equal to B for all positive T. Now, a quantum Markov semigroup is irreducible if it has no non-trivial subharmonic projection. Trivial subharmonic projection, that is mean P is equal to 0 or the identity. With the notion, you can see easily that if T is positivity unproven, then it is irreducible. Why? If T is not irreducible, there exists a non-trivial subharmonic projection P such that P different to 0 and the identity, and by using the result of Fagnola-Robledo, the subalgebra orthogonal P, BH orthogonal P is invariant under the action of TT if P is subharmonic projection. Now, for all vector psi not 0 in the range of P, and for any positive x in the orthogonal P, PH orthogonal P, you have the dot product psi TTX psi is equal to 0. It's not strictly positive. And this is the contradiction with positivity unproven. So if T is positivity unproven, then it is irreducible. Now you give you the connection between the classical Levy-Einstein theorem and the notion of positivity unproven semigroups. To this end, you begin by discussing the relationship between a classical and quantum Markov semigroup. Let PIGT the transition probability at time t of a classical time continuous Markov chain xt with values in a quantable set I for all pair ig in I. You say the classical Levy-Einstein theorem, the transition probability PIGT either are strictly positive for all strictly positive T or vanish for all strictly positive T. And it is well now, if you look the result in the book of Chang and Li, if the function PIG are continuous at T is equal to 0, that is mean the limit of PIGT when T goes to 0 is 1 for EI equal to G, and the limit of PIGT is equal to 0 when T goes to 0 for I different to G. Then the limit of PIGT divided by T for I different to G, and the limit of PIIT minus 1 divided by T when T goes to 0 exists. The first is non-negative and finite. The second is non-positive and can be equal to minus infinity. Here, you suppose now, in this talk, you suppose that f of QII is strictly bigger of minus infinity. With this assumption, you can define the classical Markov semigroup TT in the commutative algebra of bounded function on I by TTFI is the sum of transition probability PIGT FG, which is norm continuous because f of QII is strictly bigger minus infinity. And its generator of the classical Markov semigroup Q is the bounded operator defined in the set of bounded functions in I by QFI is the sum of QIG FG. Now, if you take H, the Hilbert space of complex valued square summable sequence with canonical orthogonal basis EI. So, for all IG in I with I different to G, define the operators LIG is equal to the square root of QIG the bracket E, G, E, I, and G is equal minus 1/2 sum of L-I-G star L-A, L-I-G. And you take H is equals 0, the operator 0, and consider the quantum Markov semigroup generated by L, represented in GKSL 4 with both L-I-G and G. A straightforward algebraic computation shows that you have this relation, the relation between the generator, the infinitesimal generator of quantum Markov semigroup and the infinitesimal generator of classical Markov semigroup. By this relation, LMF is equal MQF, when MF is the multiplication operator defined in H with value in H for every G associated F type G. So this is the relation between the infinitesimal generator of quantum Markov semigroup and the infinitesimal generator of a classical Markov semigroup. Now, the probability transition from I to G in time t of the classical Markov chain satisfied is equal the dot product EI TT of the bracket EG EG EI is equal the dot product EG T index star T of the bracket EE EE EG. So if the quantum Markov semigroup is positivity improving, then PIGT is strictly positive for every IG. And so you have the classical, the Levy theorem, and you have the irreducibility of Markov chain XT. This is the connection between positivity improving and the classical Markov chain. Now you give you the support projection of the state under the action of positivity improving of quantum Markov semigroup. You have here two results. Theorem 1, let T be a non-continuous quantum Markov semigroup, positivity improving on BH, with generator L as in GKSL form and GKSL representation. And let PT is ETG for every unity vector psi with H, and for all strictly positive T, the closed linear span of vectors 5, PT, psi, PS1, LL1, PS2 minus S1, LL2, etc., LLN, PT minus SN, psi, is equal to the Hilbert space H for all integer n for all S1, S2, Sn, and L1, L2 satisfy this inequality. The proof of this result, let T be a norm continuous quantum Markov semigroup, positivity improving. Then, for any pure state psi, the support of the state T index star equal to the Hilbert space H. And a sample argument of analyticity of the semigroup PT lets the characterization of the support T index star of the bracket psi is the closed linear span of the vector 5. For the proof of this result, you can see the paper of Fagnola, Robbiletto, or the paper of me. So you have the result if the support projection, if the quantum Markov semigroup is positivity improving, the vector or the span, the closure span generated by the vector 5 is H. Now, you have this definition to give you another characterization. For all pure state W is equal bracket psi, you denote by SW the closure of linear manifold generated by the vector of the form psi delta GM1 LL1 etc. delta GMN LLN psi, this form 6. And what is delta Gn is defined recursively by delta G0A is equal A, delta G1A is the commutator between G and A, etc. Delta Gn plus 1A is the commutator between G and delta Gna. Now, define R as the closure of the linear span of the set of operators identity delta G M1 LL1 etc. delta G Mn LLN. So now we give you the second characterization. Let T be a norm continuous positivity and proven quantum Markov semigroup on BH with generator L as in GKSL representation for all vector in H not zero. C is cyclic for the set of operator R. That is mean SC is equal to helper space H, where SC is defined in the previous sex. The proof of this, let T be a norm continuous quantum Markov semigroup, positivity and proving, for any pure state psi the support of the state T index star T of the bracket psi is equal to the helper space H by the previous proposition. And if you take the result of Fagnola, Robledo, or me, the support projection of T index star T of the bracket psi is the linear manifold PTS psi, and by the invertibility of PT, you have S psi is equal H. Now we discuss the channel example of a channels or discrete time case. This example is irreducible but not positivity and proven. So the situation is radically different for channels, namely in the discrete time case, as shows the following example. By the previous remark, positivity and proven implies irreducibility. The converse, however, does not hold. If you take H is equal CD, with D is greater or equal 3, with canonical orthogonal basis E1, E2, etc., ED. Now, you define the operator N and S by N EG is equal G EG, and SEG is equal EG plus 1 when G is between 1 and T minus 1, and SED is equal E1. Now, you can define the operator V1 is equal S sine of 2 pi n divided by D plus 1. V2 is cosine 2 pi n divided by D plus 1. And consider the completely positive unitary map on MDC. Phi x is equal sum k is equal 1 to 2 Vk star x Vk. Note that V2 is self-adjoint with the sample spectrum because the function defined in the finite set 1, 2, etc. d by g associated cosine 2 pi g d divided by d plus 1 is injective. So you have sample spectrum here. Now, if you take P is a subharmonic projection, by using the result of Fagnola, Robledo, you have V2 pi, P is equal P V2 P. And if you take the adjoint of this identity, you prove that V2 and P commute. So V2 and P is the diagonal matrix in the basis, in the canonical basis E1, E2, etc. ED. So P can be writing sum of the bracket EG, EG, when G is G, and G is subset of the finite set 1, 2, etc. D. Now, another consequence of subharmonic projection by using the result of Fagnola Robledo, you have the orthogonal P, V1, P is equal 0. So the sum of sine 2 pi G divided by D plus 1, the bracket EG plus 1, EG is equal to 0, but this coefficient is different to 0 for all G in the set 1, 2, etc. D. It follows that there is no G in G such that G plus 1 is not in G. So G is equal to the anti-set or the full set, and this is proof that phi is irreducible. But here, phi is not positivity improving, because if you take one project or rank one projection P, the range of phi P is at most 2, and so it is strictly contained in CD, so phi is not positivity improving. This is example of phi of example of irreducible but not positivity improving. Now, what is the condition to give a reducible quantum Markov semigroup to be positivity improving? In this cycle, you will investigate when an irreducible quantum Markov semigroup is positivity improving. To this end, you introduce the decoherence-free subalgebra of T, defined by NT is the set of all bounded operator X such that TTX star X is equal to TTX star TTX, and TTX X star is equal to TTX star for every positive T. It is well known that NT is the biggest von Neumann that is mean subalgebra of BH containing the identity and weak star closet, on which every TT acts as a star homeomorphism, and also that TTX is equal EITH E minus ITH for any self-adjoint operator of GKSR representation of the generator of TT and for all bounded operator X in the decoherence-free subalgebra of T. For the proof of this result, you can see the paper of Evans, Bahri, Fagnola, Robleto, Deschamps, Fagnola, Sasso, Emunita. Moreover, you can characterize NT in terms of operators H and LL in any GKSL representation of L. First, you can define irritator commutator like the previous definition, delta H and X recursively by this relation. So you have this result, the decoherence-free subalgebra NT is the commutant of the set of operators 9 defined. The 9 is defined by delta H and LL, delta H and LL star for any integer n and for any L greater or equal to 1. For the proof of this result, you can see the paper of Deschamps, Fagnola, Sasso, and Omineta. In this section, you consider the case where the linear span of the set of operators LL is self-adjoint, namely for all L greater or equal to 1, there exists a square summable sequence ZLK such that LL star can be written ZL0 identity plus sum ZLK LK when K is greater or equal to 1. Under this assumption, you look for a characterization of norm continuous quantum Markov semigroup are positivity improving. Before you give you this result, you give you this important lemma. If the linear span of the set of operators LL is self-adjoint, the closed linear span of the set delta HN LL, delta HN LL star for any integer n and for L greater or equal to 1 coincides with R. Remember, R is the closed linear span of the set of operators identity delta G M1 LL1 etc. delta G Mn LNL. The proof of this, let's use first check the convergence of the series sum ZKG LG delta H and LLK for the strong operator topology. And this is this sample to prove this. You dominate the general term of this series using sample properties of the dot product by sum of 2 seconds general terms of convergent series. You can look the the inequality that the norm of this general term is dominated by the square zkg plus the dot product x lg star lg x. And you have zkg is a square summable sequence, and the series sum lg star lg is strongly convergent, so it is also weakly convergent, and you have this result. Now, to show that the linear span of sets of operators 7 iterators with H and 9 iterators with G coincide for all integer n denoted by Gn, respectively Dhn, the linear span of the identity and polynomials of arbitrary degree in operator LL and iterator commutators delta Gm and L, respectively delta H M L L of order m less or equal to n. Clearly, dj0 is equal to h0 because both sets continuous identity and polynomials in operator L and by self-adjoints of the linear span of LL continuous LL star. Suppose that dgn, dhn coincides for a certain n, and note that Lk star is the sum of z kg lg, and by the relation between g and h, you can write delta gn plus 1 ll in function of delta h, delta gn, etc. So you have delta gnl is in the hn, so delta gn plus 1 ll is in the hn plus 1, and you have the first inclusion. In a similar way, starting from delta hn plus 1 by using the relation between h and g and the self-adjoint operator of nl, you can check the reverse inclusion and the proof is complete. Now, finally, you have this result. Let T be a norm continuous quantum Markov semigroup on BH. If the linear span of the set of operators LL is self-adjoint, then the following are equivalent. First, T is positivity and proving. Second, T is irreducible, and T is trivial. If T is positivity and proven, then it is irreducible. Suppose now NT is not trivial. So there exists a non-trivial projection P such that TTB is equal EITHB E minus ITH for all positive T, so that the kernel of TTB is not reduced to the zero for all strictly positive T. And this is the contradiction with positivity and proof. So it is necessarily NT is trivial. Conversely, NT is trivial. The commutator of the set of operator 9 is trivial. So by using the result of Bartelli-Robertson, every non-zero vector C in H is cyclic for the set of operators 9. The proof is complex if you know that under the assumption that the closed linear span of the set of operator LL is self-adjoint, the linear span of the set 9 defined by H, iteration by H, coincide with the linear span of the set of operator defined by iteration with G coincides. So the vector psi is cyclic for R, and the support projection of any initial state omega under the action of quantum Markov semigroup T is H for all strictly positive T. So by the previous proposition, T is positivity and proven. Thanks for your attention.
Thank you, Professor Skander, for this nice talk. Please, are there some questions? Can you go to the first 2 or 3 slides, please, Professor?
Number 2, number 3.
Maybe number 2.
Number 2. Here?
Again, please.
Hmm?
Yes. Why the norm of A star is not the norm of A?
What?
The norm of A star.
But necessarily. In the general case, not necessarily.
Because the star of the star is the initial vector. I don't know. Just I have a general question. Why quantum probability? Why the word quantum? Where is the quantum in this topic?
The classical Markov semigroup not solve any problem in mechanics, for example, when the operator not commute. We say that the classical Markov semigroup defined in the set when the function commute, but quantum Markov semigroup, the quantum probability is the generalization in the set, but not necessarily commute.
Okay. Have you some applications of quantum probability? Some real applications?
Yeah. For example, for stochastic Schrodinger equation with the operator, for master equation, if the operator not commute, etc. For the equation differentiable, when the equation differentiable is defined by two operator, not commute.
Okay, I mean by application, real application in biology, for example, or in physics, where we can apply the quantum probability.
Exactly, I don't know, but I see that there is many application in quantum mechanics.
Okay.
This notion of bracket and the bracket, the notion of a bracket is usually defined by in physics quantum, in quantum physics.
Okay, thank you. Okay, probability measure here. If we go back, please. Yes, no.
Here?
No, the slide where we have the property of the probability.
The table?
Yes. Here rho is a diagonal matrix where we have in diagonal P1, P2, Pn. Sure, the summation of Pn equals 1 or not? Or not the sum? The sum, yes. The sum
of pk is the sum of probability is equal 1.
Okay. Other questions, please? And then some questions. No question? Okay, if no questions, we have to thank again Professor Skander for this nice talk. And
thank you. I have another question.
Yes, Dr. Wissam, yes.
Just on the slide, when you say mean value, the expected value of x equal the sum of what? X of omega k, right?
No, sum of pk x omega k. Yeah.
This is not the usual way to define the expectation, right?
In the finite set, when omega is the set W1, W2, etc., Wn, cardinal of omega is n. In this example,
okay.
pk is the probability of the singleton wk, and it's
It is exactly the known mean that we know for the general probability. In the summation of okay, it's exactly the same. I think that exactly the same formula.
Yeah, the same formula.
And here we have okay, mean value, quantum probability, and Kolmogorov probability. Okay, the mean is exactly the same for Kolmogorov probability and quantum probability. Exactly the same formula. The mean value in this table, the mean value is exactly the same as for Kolmogorov probability and for quantum probability. Yes?
Yes, trace of rho x is the expectation, is equal to the expectation.
So the notation e to the power capital P and e to the power rho is exactly the same same formula.
Yeah.
Okay. Some other questions, please. Okay. Thank you very much, Professor Skander.
Thank you.
And see you next week with Professor Marco. Thank you. Bye.
Bye.